So this is an introduction to enthalpy changes, and also we're going to be looking at enthalpy profile diagrams as well. Enthalpy changes and enthalpy profile diagrams. Okay, so first thing is an introduction. What I want you to do is I want you to imagine lighting a Bunsen burner. Okay, so you've got your heat-proof mat out, and you are going to light a Bunsen burner. Okay, as you're lighting the Bunsen burner, I want you to think about all the things that are happening to do with the chemistry, to do with energy as well, in terms of chemistry, in terms of the chemicals, in terms of energy, what is happening when you light the Bunsen burner. So pause the video now and then write down everything that's happening when you light a Bunsen burner. Press pause. Okay, so let's see, what have you come up with when you light a Bunsen burner? Okay, when you light a Bunsen burner, it gets hot. There's flame. Let's go into a bit more detail. Okay, which chemical is burning when you light a Bunsen burner? What's the chemical that comes out of the gas tap? The chemical is methane. And methane is a gas, and that's what comes out of the gas tap. Okay, and then when you burn, when you combust the methane, combustion reaction, it's burning with oxygen in the air, and you are forming, this is when you're lighting a Bunsen burner, you're forming what? You're forming carbon dioxide gas and water. And then we just need to balance that equation. So there's one carbon, 4 hydrogens. So we need to have here, there, so we've got 4 hydrogens. And then oxygens is 2 oxygens, 2 oxygens. That's 4 oxygens in total. So you need to put here 4 oxygens. So 4 oxygens in total. So whenever you're balancing these kinds of equations, you always balance the carbons first. Balance carbon first. Then you balance the hydrogen, and then you balance the oxygen. This is when you've got a combustion reaction. That's how you balance the equations. Okay, so this is actually the chemistry of what's happening when you burn a Bunsen burner. When you light a Bunsen burner, the methane coming out of the gas tap is combusted to give carbon dioxide and water. All right, it is an exothermic reaction, which means that energy is released to the surroundings. Yeah, so when we think about the term exothermic, if we have a reaction, let's take a flask. Okay, we've got a flask, a conical flask. Okay, and we've got some chemicals in there. Okay, and then those chemicals are called a chemical system. And when a reaction happens and energy is released to the surroundings, the surroundings means the solution. It means the glassware, and it also means the air as well around. Okay, so exothermic is when heat exits. It goes out from the chemicals to the surroundings. That's the solution, the glassware, and the surrounding air. Okay, whereas endothermic means that heat enters the chemicals. So endothermic, if you've got a flask, if you've got a flask and you've got some chemicals in there, that the energy enters the chemicals from the surroundings. So the surroundings will feel cold, will feel cooler, will feel cold, because the energy is going into the chemicals. Whereas for an exothermic, the surroundings, the solution, the glass with the air, will feel warm, because the energy is coming from the chemicals to the surroundings. Anyway, so lighting a Bunsen burner is an exothermic reaction. Okay, so does it just happen by itself? If you open the gas tap, does the reaction just happen by itself? No, you need a spark, you need some energy to get it started. Okay, you need some energy to get it started. Why do you need energy to start the reaction? Why do you need energy to start the reaction? Because you need to break the bonds. Talk about that a bit more in a moment. Okay? Finally, what's happening in terms of energy? When you're lighting a Bunsen burner, what is happening in terms of energy? So we have got energy being, we've got heat energy coming out. Yeah, when you light a Bunsen burner, you've got heat energy. You've got light energy. Maybe you've got a bit of sound energy as well. Major one is heat energy. Okay, and the first law of thermodynamics, or sometimes called the law of conservation of energy. Energy can be neither created nor destroyed. It's just transformed from one form to another. So if we've got heat energy being made when you light a Bunsen burner, then that energy must have come from something, because energy cannot be created nor destroyed. It's come from the chemical energy. And that means the energy, chemical energy, is the energy stored in the bonds. Energy stored in the chemicals. Energy stored in the chemical bonds. When you light a Bunsen burner, that chemical energy is being converted into heat energy, light energy. Now for chemistry, we're not really bothered about the light energy. We don't pay much attention to that. We look at the chemical energy being converted into heat energy. Does it get hot? Does it get cold? And this term for chemical energy, the word we use for chemical energy is that we use the word enthalpy. And enthalpy means chemical energy. And the symbol that we use for enthalpy is the symbol H. That's the symbol, capital H is the word, is the symbol we use for enthalpy. Okay, so let's just get a definition up. So enthalpy, and the symbol we use is capital H, is the heat content, and that's why we use H for it, heat content, the heat content that is stored in a chemical system. It is basically the chemical energy. Okay, just basically chemical energy. Chemical energy. Okay, basically chemical energy. So, an exothermic means that heat is lost to the surroundings, so it feels warm. All right, now it's not possible for us to measure the enthalpy of something. Instead, we measure the enthalpy change. Enthalpy change, and we use this symbol. Okay, so we've got, this is a capital, this triangle is a capital delta. Okay, so you've probably come across a small delta already, a lowercase delta, which in chemistry means slightly positive, slightly negative. This is a capital delta, and we use that to mean change. So this is change in enthalpy. So from the start to the end of a reaction, what has been the change in the chemical energy, change in enthalpy? And we have what the enthalpy is at the end, the products, take away the enthalpy of the reactants, products, reactants is the change in enthalpy. And change in enthalpy is always measured with the units kilojoules per mole. So that's a small k, that means kilo, thousand, joules per mole for every mole. Okay, and we measure enthalpy change. Right now, in terms of enthalpy profile diagrams, we're looking at the change in enthalpy as a reaction as has happened. So enthalpy profile diagrams is what we call them. Enthalpy profile diagrams. We're looking at the change in enthalpy as a reaction has happened. Okay? So if you're asked to draw this, you draw the axes. You always label the axes first. It's just a sketch. So there's no units on the axes. Okay, on this, the y-axis, we label this enthalpy. because we're looking at the change in enthalpy as a reaction happens. This at the bottom, the x-axis, we call that progress of reaction or reaction pathway. You could use reaction pathway as well. Okay, so we're looking as a reaction progresses, what's the change in enthalpy? So we're going to use the same reaction we're going to do by burning the Bunsen burner, lighting the Bunsen burner, and the gas that's being produced. Okay, so it doesn't matter where we start. We're just going to put a line here because there's no actual axes on there. I'm going to put the reactants, the methane gas and the oxygen molecules. They're the reactants of when we light the Bunsen burner. Right. So we know that the reaction is exothermic, which means that energy has been given out from the chemicals. So as the reaction has gone from reactants to products, heat energy has been given out. Okay, so the products have got less energy than the reactants have. Products have got less energy because energy has been given out, because it's an exothermic. So the products are carbon dioxide gas, water liquid, my handwriting's wrong, water liquid. The products have got less energy than the reactants. And from the reactants to the products, right to the products, you do a proper arrow. From the reactants to the products, that is called a change in enthalpy. Alright, change in enthalpy. You don't do a double-headed arrow, you just do a single-headed arrow. Okay? If we put some pretend numbers in, these are not real numbers because we can't measure it, we're just going to put some pretend numbers. If we pretend that that number is 100 kilojoules per mole, and we pretend that that number there is 50 kilojoules per mole, what would the change in enthalpy be? So these are just pretend numbers because you don't actually have the numbers. Change in enthalpy for this reaction will be the enthalpy of the products, 50, take away the enthalpy of the reactants, 100. So it's enthalpy of the products, take away enthalpy of the reactants, which equals minus 50 kilojoules per mole. So how do you know if a reaction is exothermic? It will have a negative, exothermic means a negative enthalpy change. Okay, negative enthalpy change. And the number is just a made up number. Okay? So whenever you have in chemistry, you have a chemical equation. So let's go back to that same chemical equation again. You've got a chemical equation and you're thinking, oh, is this an exothermic or is it an endothermic reaction? At the end of the chemical equation, there'll always be something like this. Delta H equals minus, whatever the number is. Let's just put X, whatever the number is, kilojoules per mole. And when you see a minus, that tells you it's an exothermic reaction. that tells you that the reaction gets hot, the temperature increases, because energy is going from the chemicals to the surroundings. The surroundings are getting hot and the temperature increases. Okay, so this is for an exothermic. So we're doing the reaction that we mentioned at the start. Okay, now we said that some energy is needed. You need a spark. When you light a Bunsen burner, you need a spark. You need something to get the reaction started. And that's because you need to break some bonds. And this is called the activation energy. So just write definition again now, another definition, activation energy. Activation energy, which has a symbol that we use in chemistry, EA, is the minimum energy needed, to start a reaction, by the breaking of bonds. It's called activation energy. Okay, and that's the spark, that's the match that lights the chemicals. It gets the ball rolling, gets the bonds broken, gets it started. And the way we represent that on the enthalpy profile diagram is we represent it as an increase in enthalpy provided by the match. Increase in energy provided by the match. Okay, so no arrows, just a energy barrier like that. And the activation energy is always from the reactants to the top. That is the activation energy, EA. Just got a little note here. Activation energy is from the reactants to the top of the energy barrier. Okay, so the molecules need an increase in some energy to get the bonds broken, and then once the energy's been released, you can go on to form the products. Okay, so let's just quickly look at an endothermic. That's an exothermic. Let's quickly look at an endothermic reaction. So a well-known endothermic reaction is this one here. So which is what you did for GCSE, is if you take calcium carbonate, commonly known as limestone, and you heat it up, you get calcium oxide and carbon dioxide. So you need an input of energy. You need to heat it up, and that's called the thermal, because you're heating it up, decomposition, because it's breaking down, of calcium carbonate or limestone. This is a common name. Okay, so that is an endothermic because heat is being put into the reaction. So again, you start with your axes. If you're doing the enthalpy profile diagram, this axis is labeled enthalpy. This axis is labeled progress of reaction or reaction pathway. And it doesn't matter where the reactants are. I'm just going to draw them on a line. Calcium carbonate is the reactants. Okay. Now you've put in energy. So the products have got more energy than the reactants because you've put in more energy. So it's higher up, they've put in energy. So the enthalpy change is from the reactants to the products, single-headed arrow, from the reactants to the products. Okay, enthalpy change is always, the arrow is always from the reactants to the products. The way you draw the arrow, it's always from the reactants to the products. Okay, if we put some pretend numbers in, if we said that this is 50, if we said that this one here is 100, okay, pretend numbers, the enthalpy change will be delta H equals the product, HP, product take away reactant. So product is 100, take away the reactant, which is 50, so that equals 50 kilojoules per mole and that's a positive number, So positive enthalpy change is an endothermic reaction. So by the side of this equation, I could write delta H equals a positive number, whatever that number is, we don't know exactly what it is, kilojoules per mole. Okay, the activation energy is an energy barrier like this, and it is always activation energy is from the reactants to the top, and that's the activation energy. Okay, so you notice for an endothermic reaction, this is an endothermic reaction, so it's very clearly endothermic reaction, that the activation energy is a lot larger than a exothermic reaction.